Hi guys, let's do find if path exists in graph. So there's a bidirectional graph with n vertices where each vertex is labeled from 0 to n minus 1 inclusive. The edges in the graph are represented as a 2D integer array edges where each edge at I equals u of I, comma v of I denotes a bidirectional edge between vertex u of I and vertex v of I. Every vertex pair is connected by at most one edge and no vertex has an edge to itself. You want to determine if there's a valid path that exists from vertex source to vertex destination. Given edges and the integers n, source, and destination, they want us to return true if there is a valid path from source to destination or false otherwise. So in example 1, we're given this graph. We have 3 nodes here, and we are given this array of edges. Our source is 0 and our destination is 2. So we want to start at 0 and get to node 2 basically. And we can return true because we can actually get from 0 to 2. We can either go directly from here or we can go from 0 to 1 to 2 this way. And then in example 2, we have 6 nodes here, as we can see. This is our array of edges. Our source is 0, our destination is 5. So we want to get from node 0 to node 5, but we can't actually do that, so we output false, because basically we're going to traverse from, we're going to start at 0 and then realize that there actually is no path to get to 5 from 0. So we would return false. So for this one, we can do a DFS where we start at whatever our source node is, which in both of these cases it's 0. And let me see. Yeah, so in both these cases it's 0, but I guess it could be anything. And we want to do a DFS. You could also do BFS, but starting from this node and then see if you can actually get to your destination node or not. And we'll do that by having a set to keep track of the nodes that we have visited so far so that we don't end up revisiting a node twice. Also we're given an array of edges, which, if you guys remember, is not the best format when working with graphs. So we're going to want to convert this into a map where we are mapping each node to all of their neighbors so that we don't need to traverse through this array every single time to visit all of, to see what all of its neighbors are. And instead we can just do a quick lookup in the map to get that. So we're going to start out by building our map. So we're going to say map of integer to a list of integer. Graph is new hash map. And then we're going to want to loop through our edges array to build out this map. So for, actually we're just going to do by node, I guess, because each index is the node. So I'm just going to do by array instead of by index, because we don't really need the index here. So for each inside array in edges, so we are going to want, okay, let's also visualize what our graph would look like. So currently it's empty. And then we want to, so if we're at this first array, we're going to want to map 0 to 1 and 1 to 0 because we have okay, so I guess I pasted example 1 here. So basically we're going to want to map 0 to 1 and 1 to 0 in our graph because these are neighbors of each other because it's an undirected graph. So first we're going to have to add an empty list. So graph.putifabsent edges at 0 because at 0 is this one and then at 1 is this one because those are the indices. Sorry, I can't speak apparently, of the inside array here. So we're going to put that with an empty array list. And then we're going to do the same thing for this one. So okay, and then once we've done that, then our graph is going to look like this. So 0 to nothing and 1 to nothing, like an empty list, because that's what we have added so far. Okay, and then once we've done that, then we want to actually add the values to each array list. So then we're going to say graph.get edge at 0 dot add edge at 1. So if we get edge at 0, that's 0. So then the graph at 0, then that's going to be this list. And then we're going to add edge at 1, which is this one. So we'll add 1 here. And then we'll just do the same thing for this other one. So graph.get edge, oops. Apparently I can't spell today either. Dot add edge at 0. Okay, and then that is going to just do the same thing but the opposite, right? So like edge at 1 is this. So for 1 in the graph, the key 1 in the graph, we are going to add edge at 0, which is this 0, into this array list. So it'll look like that. Okay, and then we're going to do the same thing for the rest of this. So if like when we get to this array next, in the next iteration, then we already have a key for 1, so we're not going to do anything up here. But for 2, we don't have that yet, so we will have 2 mapped to an empty list here in this one, and then we're going to map this number to this number. So we're going to add 2 here, and then for 2, we're going to do the same thing. We're just going to map that to 1. And as we can see, that is accurate because we have an edge from 2 to 1 and from 1 to 2 because it's bidirectional basically. And then when we get to this one, then we're going to also map 2 to 0 and then 0 to 2 like that. So then this is what our graph will ultimately end up looking like at the end of this loop. And then once we've done that, we can create our set to start our DFS. So like to keep track of the nodes we have visited in the DFS. So we're going to say set integer visited is new hash set. And this starts out empty. Okay. And then we will just do a DFS and return whatever this DFS returns. So like if we were able to visit the destination node or not from the starting one. So we're going to return DFS and we're going to start from the source. So we're going to need to pass in the source, the destination, the graph, and visited. And that is because so we're starting at the source, so we need that in the DFS. We need to know what the destination is in the DFS because like we're going to have to do a DFS from every single node. So we're going to have to know which node we're starting at and ending at in the DFS. We need the graph because we need to be able to access whatever our current node's neighbor is to know what node to get to next. And we need visited because that's how we're going to exit our DFS, is if we've already seen that node or not. So yeah, so now we can create our DFS method. So private, we're going to return a Boolean because it's going to be if we were able to reach that destination or not. DFS, we're going to pass in. So instead of source, I'm going to say current because source is just where we start. So that's what we're passing in to start with, but it's actually going to be changing because this is whatever our current node will be from each DFS. And then int destination, map of integer, list integer graph, and set of integers visited. Okay. And then our base case here when we would exit our DFS is going to be, so there's like 2 conditions. So 1, our current node is the same node as our destination, which means we've reached our destination, right? So like if our destination in example 1 is 2, then we did a DFS, let's say we went from 0 to 1 to 2 and our current node is 2. We check if this current node, which is 2, is equal to the destination node, which is 2, and if it is, then we can return true, we have reached our destination. So that's one possibility. If current is destination, return true. Okay. And then our other possibility is that we've already seen this node before. So like let's say we're in example 2 or something, and we're trying to get to 5, but obviously our current can never actually equal our destination as we can see here, but the algorithm doesn't know that. So let's say we did a DFS from 0 and we got to 1, and then we realized 1 has no other neighbors, so we backtrack to 0. And then from 0, then we visit 2. And then from 2, there's no other neighbors, so then we are trying to go back to 0. But then, like, basically, like, if we've already seen it, then, like, we don't want to, like, keep going back and forth because, like, so we backtrack to 0, okay? And then from 0, then we see that the neighbors are 1 and 2, but we don't want to revisit these because we already did the entire path from these nodes, so it would be redundant to, like, keep going back to them. So we can, like, basically prune off this path because we know it doesn't actually work. And then if that's the case, then this will return false. So if visited contains current, then we'll return false, okay? And then if none of these cases are true, that means we're still in our DFS. So we will add our current node to visited. So visited.add current. Okay, and then we'll do a DFS on all of their neighbors. So let's say for each neighbor in, so let's pull this down so we can see better. So for each neighbor in, so like we're starting at like say, 0, right? Then we want to loop through 0's neighbors, which are 1 and 2 here. So for each neighbor in graph.get current, that's going to be looping through this list of neighbors, okay, and doing we're going to do a DFS on that. So if the DFS on this neighbor returns true, so we'll pass in neighbor, destination, graph, and visited, then we'll return true. Okay, and then if we go through all of their neighbors and none of these are true, then we will return false. So let's test it. Oops. Oh, typo. Sorry about that. Okay. Okay, there we go. Sorry. Okay, so basically, then our time complexity here is O of n plus e, where n is number of nodes in the graph and e is number of edges in the graph. And this makes sense if we think about this logically, right? Because basically, like, let's say in example 1, we start at 0, and from 0 we do a DFS, we visit 1 and we visit 2. Then we basically have to visit every single node and every single edge in this graph, right? And in example 2 we don't, but like, so I guess worst case would be that it actually returns true, because then we may actually need to visit every single node. Otherwise we don't and we exit early. But yeah, so that's why that's the time complexity. And then our space complexity is going to be the same thing. Oops. And that's because, so if we take a look at what our actual data structures here are, we have the graph, which stores every single node here and every single node's neighbors, okay? And so that's like basically like, I guess, an edge. And then we have our visited, which only stores each node once, so that's O of n. And those are our only data structures. So yeah, thank you guys for watching, and like and subscribe if you found this helpful. Bye!